Yeah, thank you for the introduction, and I want to thank the organizers for giving me the opportunity to present this work, which is part of this very big paper on more general anyon condensation protocols in the color code, which was a collaboration between University of Sydney and Freie Universität Berlin, where I'm currently doing my PhD. Before I start how anyon condensation is described in stabilizer models, and in particular in the color code, I want to make a comment on how we think about storing logical qubits over time. Traditionally, people thought about mostly encoding a logical state into some fixed code space described by a stabilizer group, and then the associated error correcting protocol is defined by projectively measuring onto some generating set of the stabilizer group. And you might need to repeat this over time, but the key thing is it's the same stabilizer group, same code space. And what we've heard in this conference already in several talks is that it's actually helpful to think a bit more generally of more dynamical protocols where you don't care so much about the logical state, but more about the logical Pauli group and some initial representation of the logical Pauli group that then evolves through your protocol in some way. You might even change the number of qubits during the way or do whatever. And as long as you understand how your logical Pauli group is affected during this protocol by noise and by measurements that you do, you can still infer the logical information with some guarantee on fault tolerance. In this talk, I want to tell you how such dynamical protocols can be designed using anyon condensation for dynamical protocols defined on or based on topological code, such as the Floquet code that we saw in the last talk. I will try to not go too much into the not error correction theory behind it, but still I want to show you a bit about the more general framework that falls into which anyon condensation falls in abelian anyon models. For this, I have to tell you first what they are, and then how condensation looks in this model abstractly and also on the level of the stabilizer model, where it becomes probably more interesting for most of you in the audience. In the end, then I will show you how we can understand Floquet codes as dynamically condensed codes. So an abelian anyon model is a model describing so-called one-dimensional deconfined defects in these 2+ one-dimensional topological phases, and you can think about them as being like world lines of particles moving around, and secretly most of you will have dealt with them or seen them at some point when you look at decoding graphs. And for abelian anyon models, they are described by a finite abelian group capturing the behavior of like what happens when these world lines meet in space-time and then collectively move. But since these lines can like non-trivially link, they also are equipped with a braiding, which is in this case captured by number called the topological spin. This then defines this braiding phase, and which has to be consistent with the fusion described above. So this non-trivial relation between these two quantities defines an abelian anyon model. And some would call an anyon where the topological spin is 1 a boson, if it's -1 a fermion. In principle, it can be many different values, not just 1 and -1. For this talk, there will only be bosons and fermions, though. Okay, and most of you will have seen an anyon model, maybe not in this level of abstraction, but the toric anyon model is kind of the simplest anyon model that can be realized by a two-dimensional stabilizer code described by the abelian group Z2 cross Z2. It has two generators, which we can call E and M. The joint element is F and we call it F because the associated topological spin of that anyon is -1. And the toric stabilizer model is a specific lattice realization where you can think about certain strings of Pauli operators mimicking the behavior of these world lines that are defined abstractly on the left-hand side when they act on the code state of this stabilizer code. Condensation in abelian anyon model is a way to derive in a sense, smaller anyon model, which we call child model, from a bigger anyon model, the parent model. And it's solely defined, so given the parent model on the left, defined by some group and spins, you condense an object B, and that uniquely defines what the child theory will be. And the child theory, to obtain which child theory you will obtain, you follow a 2-3-step process. So this condensable object for the abelian anyons will be a bosonic subgroup, so a subgroup of the anyon model only consisting of bosons. And we now impose that on the level in the child model, the world lines now should be equivalent if you attach this boson or remove it freely. This defines an equivalence class on this group. You can sort them into cosets, and the anyons of the child model will be a subset of these equivalence classes. Because an anyon model is not only a group, but also this spin, these equivalence classes have to have a way to have a unique theta prime attached to it. And for anyon condensation, this theta is related, just inherited from the parent phase. And this can only be done unambiguously if the topological spin within an equivalence class is the same. If we look at this formula depicted on the top right, we can easily see that this is equivalent to saying that we have to remove all the equivalence classes for which at least one of the representatives braids non-trivially with at least one element in this bosonic subgroup that we chose to condense. We can summarize what the anyon model of the condensate is with this formula. So it's a set of equivalence classes, not all the equivalence classes. And which equivalence class we keep and which we have to remove is defined by the braiding statistics with respect to the bosonic subgroup that we condensed. The slide title said color code, so here is the first slide with the color code. So the color code anyon model is defined by, or has 9 bosons. These bosons can nicely be depicted in this 3x3 grid, where each has like a tuple of labels, one color, one Pauli label, and this table is a really nice depiction because it captures the fusion, and so how the product of this group behaves, and the braiding quite nicely. In particular, the bosons within the same row and the same column fuse to the third element in this row and column. And if you take a composite anyon of 2 bosons that don't share a column or row, they form a fermion, which is captured by the non-trivial braiding statistics shown here. So as a rule of thumb, if two bosons don't share a column or a row, they braid non-trivially. If they are in the same row or in the same column, they braid trivially with each other. So if we now say we want to, so as I told you, I have to pick a bosonic subgroup. So say I pick the subgroup generated by the single Rx anyon. Now we say this, if we condense Rx, we have to first remove all the anyons that braid non-trivially with it, which in this tabular depiction is very easily seen. You could just cross out these bosons, and in that removing all the anyons that are generated by them from your anyon model. And then additionally, you identify the ones that differ by the fusion of the ones that I condensed. So now the condensed anyon theory has 4 objects, namely the trivial one, like the black circle, the blue circle, and the orange circle, and its product, which is 4 elements, and the topological spin is inherited from the color code, which in this case gives rise to a toric code model. So the anyons of any, so if I condense any of these bosons in the color code, a single one, I will obtain an anyon model that's equivalent, the toric code anyon model. So for those of you for which this was a bit too abstract, now it's the time to pay attention again, because this can easily be implemented in stabilizer codes. So in the color code, you can see that that the anyon model that I defined abstractly is really represented by the lattice model. In this case, on the hexagonal grid, but you can choose any lattice for which the faces are 3-colorable. And you can see that 2 body operators of Pauli's will create a pair of violations of certain stabilizers that mimic this anyonic behavior. I won't have too much time to go into detail why that actually is the correct anyon model. You have to believe me at this point. But if we start with this color or code in the color code state, then and we want to condense Rx, the only thing we have to do is measure these two-body terms. What this will do is it will change my stabilizer group according to generic, to rules how to update the stabilizer groups when you do Pauli measurements. Namely, first, you take the group of short string operators, like the group generated by the things you measure. Then you remove the non-commuting terms, which relates to the confinement that I talked earlier about. And then you take the union of what was commuting in the original stabilizer group with the group generated by all the measurement terms. So this is now a new stabilizer group. We call it the condensed stabilizer group, in this term, the one that we obtained by condensing Rx. And an important point is that it also contains non-trivial loops of the anyon strings that I condensed, right? Because I can form any non-trivial loop of this anyon string operator associated to this boson by combining these short string operators. So how do I see that it's a toric code? The way we see it is that we look at the string operators, like which ones are stabilizer equivalent and how do inequivalent string operators commute. And we can easily see that in this particular case, you have two types of generating string operators where we can denote the associated excitations, in a sense, by E and M, and you can see that they pairwise anti-commute and mutually commute, so they form the toric code anyon model. And if you compare it to the stabilizer code that we started with, we see that a string operator that was a not a pure pair-creating string operator in the color code is a pair-creating string operator in this condensed phase because we identified certain string operators with each other. So in this case, this manifests by removing the Z plaquettes on the red plaquette. The Z red plaquettes. But importantly, all the string operators are fully inherited from the parent. So if we know all the logical operators of the color code, we can condense any boson, and we will know what the string operators of this condensed stabilizer group will be. And we know which ones become equivalent and which were inequivalent before. Now, the idea of dynamical condensation is that we dynamically go through different condensates of the color code and think about this is also more generally, but like the Floquet codes that we have seen mostly, especially in the early literature, are essentially going through these different condensates. And to understand how we can construct such a sequence in order to preserve our logical information, we have to look how the logical Pauli group evolves. So on the right-hand side, I depicted such a dynamical condensation in space-time where you have two regions. So you start with one condensate, and then you somehow want to go to a different condensate. And as in any 2D topological code, the string operators give rise to the logical Pauli group. So if we know what happens to the string operators in this dynamical protocol, we know what the logical Pauli group does. So in the so if we condense a string, I told you earlier that a previously non-trivial string after condensation becomes associated with a trivial, like logically trivial string, and this is really stabilizer equivalent in the way we implement it. So it's quite simple to see that once you have gone through this construction, and this gives rise to a very simple condition on how you can preserve logical information through these dynamic condensations. Namely, you should not, like the condensate you want to go from, like say you condensed B, and you want to go to B prime, the thing you condense should not be a logical operator of the condensate that you started with. So any element in B prime has to be confined in A B prime to make it a bit more formal. And vice versa, of course. These are reversible transitions. So in the color code, we have nine possible ways of condensing. And if we say we start with this condensate, now to preserve logical information, we are allowed to pick one of the four condensates associated to each of the 4 crosses in this leftmost table, namely one of these 4. So macroscopically, we have the choice of these 4, and for each choice then, because then we are in a new stabilizer group in a different condensate and we play the same game, which gives rise to this tree-like structure. And there is a caveat, though, to this. This only describes a process where you go from the stabilizer group of your condensate to the stabilizer group of your other condensate. This does not necessarily define a fault-tolerant low-weight protocol, as in you only measure these 2-body terms. However, we find that many do, and we have a kind of microscopic understanding in terms of the color code stabilizers. And so if you take, for example, this sequence of only Z and X measurements, 2-body terms, with period 6, this goes through different condensates, and you will see that from each adjacent pair fulfills this condition that I showed on the left. This defines a CSS type Floquet code. This is just one instance. We find many more. And this dynamically condensed CSS code was also presented in this other paper by Margarita, which will give the next talk. It dynamically goes through the stabilizer groups of these 6 different condensates after some one initialization period. We also find, using like the detector error model or outcome code, whatever you want to call it, under very simple phenomenological noise model threshold, which is closely related to the threshold of the surface code under similar noise models. And yeah, we called it Floquet color code, but I would say that's maybe not the best naming choice. And people have called it differently because the stabilizer group of any time step are in the toric code phase. So you could call it CSS Floquet toric code, whereas the honeycomb code would be like a non-CSS version thereof. Or you could call it Z2 Floquet code, or you can call it CSS honeycomb code. Unfortunately, the literature has not settled on a name, but I want to give it this. And if you have a new naming suggestion, go ahead. So, I hope I've convinced you that this is a very systematic way to understand how to construct candidates for these Floquet codes based on anyon condensation, and then how to use tools described in other talks earlier in this conference to investigate the fault-tolerant properties of the resulting protocol. There are other constructions of Floquet codes in the literature, and I want to stress a few useful properties if you construct them from a dynamical condensation sequence. Namely, the lattice and the locality, since it's so easily implemented in the lattice by just measuring short string operators, is fully inherited from the parent. Moreover, you immediately know what the stabilizer groups have to be at any time step. And we find that for many examples, it's helpful to construct boundaries through the sequence, especially when the logical operators change their type and some non-trivial action is performed on them within a cycle. And in any such approach, because it's stabilizer-based for any abelian topological code, the fault-tolerant properties can be analyzed via the detector error model or outcome code. And there's a very nice depiction of the detectors in the case of the CSS Floquet code team. With that, I want to conclude with this slide. I hopefully gave you a bit better understanding of what anyon condensation is on an abstract level, but also in a stabilizer formulation. This then showed us that the toric code can be viewed as a condensate of the color code. We have many equivalent condensates, which gives rise to dynamical condensation sequences. And we used, could use the braiding property of the anyons in the parent phase to understand the evolution of logical information through such a dynamical condensation. This then fit together into defining new Floquet codes from dynamical condensation sequences. These don't necessarily have to be periodic, but this is a very nice instance of a CSS Floquet code. In the paper, there's many more aspects of anyon condensation in the color code, and we find that it's like a very useful tool to unify, in a sense, all topological error correcting schemes into +1 dimensional stabilizer codes. I cannot, should not give a talk on Floquet code without mentioning related work, because it has been many papers were coming out, and we will hear 2 more talks on the papers on alternative constructions. Some of them using the ZX calculus, where you modify like a space-time circuit representing a stabilizer code readout, and you use ZX rules to deform the circuit to obtain effectively a Floquet code that implements the same type of projection if you coarse grain. So that's what we did in this upper left paper, together with Teague, another PhD student in Berlin. But then there are also other constructions based on topological models, such as automorphism codes and fixed point path integrals, but also individual constructions based on subsystem codes and so on. Of course, there's the OG paper of dynamically generated logical qubits that shows that this is even possible and gives the first example. I also put some maybe interesting question out there related to kind of condensation and Floquet codes. If you have some idea or find it interesting, please feel free to come to me at any time at this conference. And yeah, with that, I want to thank you for your attention, and also thank my collaborators, the co-authors on this paper, for this very nice research project. And yeah, if you have any questions, go ahead.
Hello. So on the last slide with your open questions, you had this one about, can you sensibly define non-abelian dynamical codes? Can you give like a very high-level overview about why this is a non-trivial generalization?
Yeah, it's not a. I have to say, it's not a really clearly phrased question. So good that you ask. So if you think about so there are certain Hamiltonian models that tell you how to write down a stabilizer analog model for a condensed model. So, and it works in a similar way that you add kind of short string operators as additional constraints on your ground space. But how to think about like a dynamical measurement protocol based on this is not so clear, because the way that the stabilizers are formed via these checks is does not generalize straightforwardly. But yeah, I'm happy to talk about this further.
Okay, thanks.
So actually, it's a little bit out there, but the question about color code decoders. So, often when people map color codes to 2 copies of the surface code, in your language, I guess it's 2 choices of anyon condensation.
Yeah, so the Floquet codes that I presented here are all decodable via surface code decoder, because the instantaneous stabilizer groups are in the toric code phase.
Right, so my question is, if I want to take your result and try to use it to prove bounds on color code decoders that use a mapping to surface codes, is there a way to do you see a way to do that, or does it seem like a dead end?
It sounds like an interesting question for sure. And we are kind of looking into how you can use color code decoders in spacetime to maybe use them to decode Floquet codes where the ISGs are in the color code phase. So that's definitely something we are looking into. But like more generally, how this goes into proofs, I don't know really. But interesting question, I think.
Great talk, Julio. Just kind of like a service to the community. Do you have like a phase diagram of all the condensation phases?
I mean, in the color code, it's all toric codes.
Okay.
So because there is like, so you can think about any condensation as in abelian models at least as like a sequence of condensation. So you pick one boson, condense that, then you pick another. And the moment you condense two bosons that don't give rise to this dynamical condensation, you will be in a trivial phase. Similarly to if you condense in the toric code, you end up with a trivial phase. Like you will always read out a logical by measuring a short string operator in your toric code.
I see.
So there's, yeah.
Cool. Thanks.
Hi. Yeah, just wanted to clarify some wording. On one of your slides, you said we've got a choice of 4 condensates at each time, but some of them don't lead to low weight, fault tolerant, something?
Yes.
What and what did low weight mean in that?
Yeah, so what this construction guarantees you is that if you were to start with the stabilizer group shown on the left, and then you would just measure the stabilizer generators on the stabilizer group that is shown on the right, you would preserve the logical information. But as you see, the generators are kind of the same weight as the color code generators, right? What I mean by that is it's non-trivial to find a sequence that only uses 2 body terms to then drive between stabilizer groups that have higher weight stabilizers.
Okay.
So, but you could just measure the stabilizer group on the left, then the one in the middle, then on the right, then on the left, right, and so on. This would define a dynamical condensation protocol, also a Floquet code, but I mean, it's not low weight, so the whole benefit is not there, I think.
Cool, thanks.